The parallel axis theorem states that the moment of inertia I around an axis parallel to an axis through the center of mass of an object relates to the moment of inertia around that central axis I sub c by I is equal to md squared plus I sub c, where d is the distance between the two axes. A rod of length L has a moment of inertia of 1/12 ml squared for rotation around its center. What moment of inertia does the parallel axis theorem predict for rotations around one end of the rod? So let me draw a picture to kind of clarify all this stuff. So let's say we've got a rod here, and I'm just going to kind of draw a line here. Okay, here's like a rod. Maybe we're looking at it kind of from that end, right? And we're saying if we took a rotation axis, so I'm imagining this thing like spinning around this axis that kind of goes right through the center of the rod there, and that represents kind of that maybe central rotation axis. So in other words, the moment of inertia that we're given of 1/12 ml squared, where L is the length of the rod, is really the moment of inertia around this rotation axis. The question we're asking, though, is what would the moment of inertia be around a rotation axis that's at one of the ends of the rod? So instead of just spinning around its own center, the rod is kind of going around like a single propeller blade as opposed to maybe being the whole propeller, right? So the way to apply the parallel axis theorem to this is this distance here. That is really the distance that we shifted that rotation axis. So that's what is equal to d, the distance between the two axes. But since the length of the rod is L, it makes sense that d is just equal to 1/2 L. So that means if I want to calculate using the formula of the parallel axis theorem, md squared plus I sub c, right? I'll just go ahead and write that as a starting point. Then what I would want to do is substitute for d 1/2 L. For I sub c, I use 1/12 ml squared, in other words, the original one. Maybe, actually, I just realized there's maybe some inconsistency in my notation because I use capital M for the moment of inertia here in this formula, but the generic form of the parallel axis theorem has a lowercase m in it for whatever reason. So I'm going to go ahead and fix that, because maybe what I should have done is said, as I'm like sort of substituting like from the generic statement of this theorem to the specific version that applies to this case in the picture, maybe at that juncture I should have said, oh, this m really is the total mass of the rod, which we've been calling capital M, so therefore that was maybe a little mistake that I made by not doing that. Not really a huge deal, I hope we can all agree. So let's see, we got 1/2 squared there, so this is equal to 1/4 ml squared plus 1/12 ml squared, and 1/4 plus 1/12 is equal to 1/3 ml squared. And of course we did already see this formula for the end axis rod, but it's a great example to see what is the parallel axis theorem really saying. Of course it can be applied to other things as well, and there is the answer, and it looks like all the steps align with what we just did.